Welcome to week 5. This will be our final week on three-dimensional motion, which really is for the most part two-dimensional motion. And the reason that is that for a lot of motion, we can just choose our coordinate axes so that we're in 2 dimensions. Alright, so we've looked at determining whether forces are conservative. We've looked at how we use energy in 3 dimensions, and we've looked at how work is a line integral. Now this week, we're going to look at solving for equations of motion using Newton's second law, but in 3 dimensions. So that means that instead of just having F equals ma or mx double dot, now we'll get 3 sets of equations. So we have an x component equation, a y component equation, and a z component equation. And if you remember back when we did drag at the beginning of the semester, we can also write this equation this way. Alright, so your forces are vector quantities, right? So in general, this is F equals ma. And generally, we use the r vector to represent position, and we talked about this a little bit last week. So if I wrote this in vector form, it would be, okay, so for some situations, when you write out your equations, the x equation will only depend on x coordinates and the y equation will only depend on y coordinates. In some situations, this x equation may have y in it, then you ended up with coupled differential equations. And those can be a little trickier to solve. Now we're going to encounter the situation again where the math we need to do is very long and time consuming. Some people use Mathematica to avoid actually having to do all of this by hand. And this one thing I've been thinking about is if we should include teaching how to use programs like Mathematica so we don't have to spend as much time working on differential equations. So I'd appreciate your input on what you think about that. Mathematica does cost money, although I believe the student rates are not too bad. Well, it's always better to talk about everything with an example. We're going to be doing 2 examples today. The first example we're going to be doing is we're going to be looking at a charge in electric and magnetic fields. And we're going to be looking at drag in 2 dimensions. Okay, and you might say, wait a minute, why are we doing things with electric and magnetic fields in classical mechanics? The reason is that classical mechanics provides us with tools that we need in electricity and magnetism when we're looking at charged particles. The tools of classical mechanics still apply. And personally, I really love E&M, and I love to see how all of physics is connected, so I like to have little crossovers between my classes. Okay, so let's start on our first example. We're going to say that we have the situation, so we have x, y, z. There's lots of different ways to label these coordinate axes. You just always want to make sure you're following the right-hand rule to get yourself a right-handed coordinate system. Okay, so I like the system where x is your first vector, y is your second vector, z is your third vector. Your first vector is your thumb, your second vector is your finger, your third vector is the direction your palm pushes. And that'll get you in a right-handed coordinate system. And so we're going to talk about a situation where the electric field is pointed in the z direction and the magnetic field is pointing in the y direction. And we're going to start out where the initial velocity is in the x direction. So we can write that this way. Okay, and I'm using the x hat, y hat, z hat notation rather than I hat, j hat, k hat. It's my preferred notation, but it doesn't really matter. If you love I hat, j hat, k hat, you are welcome to use it. So the Lorentz force that determines how a charged particle works is written this way. So we need to figure out how to write this in 3 equations, one for x, one for y, and one for z. The first thing we need to do is to calculate v cross b. So we've done this before in my other classes. It has been a while though. Remember, you write something that looks like a determinant to do a cross product. And we've been doing this in calculating curl. So this looks kind of like calculating curl, only it's easier. So I want you to calculate v cross b. Now, while v naught only has an x component, In general, V could have x, y, and z components. So the general way to write your velocity is that the x component is x dot, the y component is y dot, and the z component is z dot. Okay, so using this information, go ahead and calculate V cross B. I know you may be a little rusty, but hopefully it'll come back. Alright, take a minute, try that out. Okay, so remember this is written as a determinant. X hat, Y hat, Z hat in the top row. So V is, so we put our V vector in the second row, and then we put our B vector in the third row. That only has a Y component. Alright, let's work this out. Okay, so we have that V cross B. Okay, now we can go ahead and plug this in for V cross B up here. And remember, E can be rewritten this way, EZ hat. So let's plug that in. Okay, so this needs to be set equal to MA, where A is a vector, or it's the second derivative of the R vector. Let's go to the next page so we have room to write this out. So what MA becomes in this case is, so it's just mx double dot, that's an x hat component, my double dot, that's in the y hat component, mz double dot, that's in the z hat component. And then we write out what we just found the force to be on the previous page. And here I'm multiplying through. Now what you do next is you match up the x components with the x components, and the y components with the y components, and the z components with the z components. So one of our equations of motion becomes, for y it becomes, okay, so what do we know so far? Well, we can see that the acceleration in the x direction depends on the velocity in the z direction. We can see that the acceleration in the z direction depends on the velocity in the x direction. So what we have here is coupled differential equations. So solving this is complicated. And we'll do it, but we'll get to that. What we do see is that there is no acceleration in the y direction. So if it were to start out with some velocity in the y direction, it'd keep drifting in the y direction. If it doesn't start out with any velocity in the y direction, it's never going to have a velocity in the y direction. So whether this is truly a three-dimensional problem or not depends on the initial velocity in the y direction. Now, on this particular case, I gave you the initial conditions that the initial velocity was only in the x direction, so it's completely stationary in the y direction. So now we've simplified down to a two-dimensional problem. But I hope you can see if I were to give you a similar situation, and I said, depending on the direction of magnetic field and electric field, but we ended up in a similar situation, that this could be a constant velocity situation. It wouldn't necessarily be a stationary situation. Okay, so the question is, though, how do we solve these two differential equations, because they depend on each other? Doing this requires doing a lot of math that we didn't even get to in math methods. I'm going to include it, but I don't want you to get so caught up in it that you can't see the forest for the trees, because I know that happens to me a lot. When I first took classes on this topic as a student myself, I would get so bogged down in the math that I couldn't see what I was doing or why I was doing it. So I'm going to come back at the end of this video and show you how to solve this differential equation. Right now, I'm going to give you some solutions here. So when you work it all out, and again, if you want to know all the nitty-gritty details, I will have that later in the video, but for now I'm just going to tell you the solution. So in this case, I was solving these equations, and I was doing my arbitrary constants as A, B, and C. And then after I had done all the work, I realized that B was already the magnetic field, so I shouldn't be using as my arbitrary constant. But my work was going to get confusing. So I stuck a prime on a B, so that you can see B prime is an arbitrary constant, unlike B, which is the magnetic field. Sorry for my notation there. But I think it's I think it's valuable for you to see when I do something that's not perfect so that you can relate to the whole problem solving process. Okay, and our solution for z. So now we want to solve for our constants. So there's 4 arbitrary constants in these solutions: a, b prime, c, and d. And that makes sense because we have 2 second-order differential equations. A second-order differential equation generates 2 arbitrary constants. So if we have 2 second-order differential equations, getting 4 arbitrary constants makes sense. That means we need 4 initial conditions. And here's what we know. As it is always convenient, set your initial position to be at the origin. Now remember, we set the initial velocity in the x direction, so that's v naught. But our initial velocity in the z direction is 0. So there's our 4 initial conditions to go with our 4 arbitrary constants. So now I want you to figure this out. I want you to solve for a, b prime, c, and d. You have these 2 equations. You have these 4 initial conditions. Back in math methods, we used initial conditions to solve for arbitrary constants. We just have more of them this time. Now you may note I've chosen to write my answers in terms of cosines and sines rather than exponentials because it's going to make this come out cleaner. My number one place to use cosines and sines like this is when I'm solving for arbitrary constants with initial conditions or boundary conditions. Okay, so go ahead and try that out. Alright, so let's work these out. I need to write the solutions again on the next page. Okay, so we have conditions for x of 0 and z of 0. So if we plug in x of 0, cosine is 1, sine is 0, t is 0, so we just get a plus c, and we know this is equal to 0. So that tells us that a equals minus c. Now for our condition z of 0, okay, well, cosine of 0 is 1, so we have minus b prime. Sine of 0 is 0, so we get plus d. That equals 0. So that tells us that b prime equals d. Well, that's nice. That means we're really only having to solve for 2 things. Now to use our next initial conditions, we need to take derivatives. Okay, so I took the derivative. Now we know that x dot of 0 equals v naught. So sine of 0 is 0, cosine of 0 is 1. So now we have b prime qb over m plus c over b equals our initial velocity. Now we take the derivative of z of t. Okay, and this is set equal to 0 when I plug in time as 0. So now our sine is going to 0, our cosine is becoming 1, so we are left with, and this gets set equals 0. Well, it's a times a bunch of constants equals 0. So a equals 0, which tells us that c also equals 0. So now we just need to solve for b and d. So b prime, and we know that b prime equals d. Okay, we solve for our constants. Oh, also, if you look at similar problems, either in your E&M textbook or in your current textbook, you'll find that QB over M is abbreviated as omega, which is nice shorthand, but I felt like writing it all out this time so we didn't forget what omega was. So if we go ahead and plug in these constants, what are our solutions? Okay, here are my solutions. What on earth do these mean? It looks gross. But again, these are B and D. B and D are just constants. They're messing looking constants, but you gotta remember, if you actually know the mass and the initial velocity and the charge and the magnetic field, these all just become numbers. So what do these equations actually mean? Just stop and think for a moment about what the motion in the x direction looks like. What does the motion z direction look like? Okay, so the x direction has an oscillation because it has a sine, and it also has a constant increase. So, it's moving back and forth, but also moving to the right generally. Whereas a z is moving up and down. If your axes are something like this. and it's offset by a constant, but it's not drifting. Okay, so if you look in your book, you'll see some formal math to show that this turns into a circle. I don't want you to get so bogged down in doing all the algebra that you can't see why that is. What's going on is that x and z are out of phase. Sine and cosine are out of phase, right? So when sine is large, cosine is small. When cosine is large, sine is small. Think about just going around the unit circle. So over on the positive x-axis, you would say that cosine is 1 and sine is 0, whereas on the positive y-axis, cosine is 0 and y is 1. So, they're oscillating out of phase. So sine and cosine are out of phase. So that means when x is large, z is small. When z is small, x is large. That makes for a circle. But there's a drift in the x direction. So it's making circles, but it's moving to the right. That's our cyclotron motion. If our initial velocity had also included the y direction, then it'd be going through the cyclotron, but also be drifting out of the page with the way I'm looking at it right now. Okay, I hope that makes sense. Let me know if that makes sense to you. There's all sorts of algebra you can use to prove that this is the shape we're making. Like, for example, you can do parametric curves. You could write, all right, I'm going to write z as a function of x. But I don't want to get bogged down in that right now. Okay, now I'm going to go back and explain how I got to the general solutions for x of t and c of t in the first place. It's kind of a big mess. I'm going to say I may ask you to do something like this on your homework, but I'm not likely to ask you to solve this math on your test just because it's pretty time consuming. Okay, let's go back to our differential equations we need to solve. Okay, so here's the deal. We have x double dot and z dot in one equation and z double dot and x dot in the other. So we need to differentiate one so we can substitute it into the other. I'm going to differentiate this one because it has fewer terms than this one. So that means we have x triple dot equals minus qz double dot b. Sorry, that double dot doesn't look very much like a double dot. Now I just want to solve this for z double dot. Okie doke. So now we want to plug in this z double dot and for this z double dot over here. And then we'll have an equation that only has x's in it. So go ahead and do that yourself. Just plug this in. Now if I clean this up, I'm going to move the QB x dot term over. Okay. This is a third order differential equation, which we never solved any in math methods. Okay, it's third order because the highest order derivative is x triple dot. It is not homogeneous. A homogeneous equation is when if you put everything that has a derivative on it on the left side of the equation, it's set equal to 0 on the right side. But this is set equal to a constant, so it's non-homogeneous equation. Okay, the first step in solving a non-homogeneous equation is solving the homogeneous equation. What that means is we just write the left side of the equation and set that equal to 0. Okay, and we want to solve this. So remember when we were solving second order differential equations like what we do for harmonic oscillators, we wrote a characteristic equation. We're going to do the same thing here. But now, instead of being r squared, r coefficient 1, we have a x triple dot term, so that goes to r cubed, and the x dot term goes to r. Now we want to solve this just like any other equation. So take a minute and try this yourself. Solve for those roots, r. Alright, well first thing I want to do is factor out the r. Well, I'm going to factor out a minus r. I don't want to deal with a minus sign. Okay, because we've done that, that means one of our roots is r equals 0. Okay, so now we have, okay, we're continuing trying to solve for r. So if we take the square root, we get plus or minus I QB over M. Okay, so we have 3 roots. Let's copy those over on the next page. And again, most books you'll see write QB over M as omega, but I don't want to lose track of what that is. Okay, so this works the same way as it does for second order equations. Now we're getting a solution. Now this time it's called the complementary solution. So we have a e to the plus or minus QB over M. Oops, don't want to forget my time. And then c e to 0. Now here's where I forgot that I had a b already, so then I have to put that prime back in. And e to the 0 is just 1. So that's just plus c. This is the, okay, and I said this is the complementary solution. So the general solution to a non-homogeneous equation is the complementary solution plus a particular solution. So coming up with a particular solution is one of those things that seems kind of random. It's not totally random. But on the right side of our equation, we have QE. So we say, well, what is QE the derivative of? QE would be the derivative of QET. So we assume that the particular solution is going to have the form of some constant times time. And we need to figure out what D is. It really is, you guess, and then you plug it in. So what you do with this is you say, well, I'm guessing that one particular solution to our differential equation is dt. Of course, it's not the general solution, but we're just guessing. So what we do with that then is we plug d of t. We plug d of t into our differential equation, which I'll remind you is, okay, so what I want you to do now is plug our solution, our particular solution dt, into this equation. So that means you have to find x dot and x triple dot. This algebra is not gross. All right, take a minute and do that. Okay, well, x dot is just d, and all derivatives after that are 0, so x triple dot equals 0. So we have 0. Oh, these q's cancel. So if we're solving for d, we just get d equals e over b. So then our full solution, which is our characteristic equation, plus our particular solution, plus our so we have our complementary solution plus our particular solution. There's x of t. So there it is. Now I rewrote this instead of using exponentials, using sines and cosines. Okay, so that gets us x of t. We still need to find z of t. Well, we know how they're related. Back in our original equations we had. And if we rearrange that, okay, well, we have x of t. So we can find x double dot of t and plug that in here. Okay, so what I want you to do is find x double dot of t and plug it in. Then we'll see where to go from there together. Alright, so if we take the first derivative of x dot of t, okay, there's our first derivative. Let's take our second derivative. The u over b at this point just becomes 0. So then if we plug that in for z dot, this whole thing gets multiplied by minus m over qb. So then z dot of t equals, okay, now z of t is the integral of this, because that's just one-time derivative. Okay, so if we integrate that, then we end up with, alright, so now we've solved for x of t and z of t in this whole long way. Again, going through this whole process is pretty time consuming, so while I may ask you to do it on homework, I'm not going to ask you to go through this entire process on an exam. I may ask you parts of it, but I won't ask you to go through the whole process. Okay, let's do our other example. And now you can see why we're only doing 2 examples today. These problems are really long and involved. Alright, So the next case we're going to do is the case of linear air resistance for a projectile. So we've done drag for falling objects, and we've done drag for sliding objects. We've done drag for springs, but we haven't done drag for projectile motion. So I'm sure you've spent lots of time with your students teaching them to do projectile motion, and you're always telling them that you're ignoring air resistance, but you know air resistance matters, right? And we've talked about this some this semester. Now we're going to look at doing that not just in one dimension, but now in 2 dimensions. Now, generally you can do this in 3 dimensions, but why do 3 dimensions when you can just say the plane of your projectile is in the x or the y direction? That's just easier to do. Okay, so here we're talking linear air resistance. I'm going to set our initial conditions so that we don't get something that's too messy. I'm going to set our coordinate axes and our initial conditions so we get something that's not too bad. So I'm going to set down to be a positive y direction. I'm going to set to the right to be our positive x direction. And I'm going to set our initial velocity. I'm going to set our initial velocity to be in the x direction. So it'll be some sort of projectile like this. So you know how, because we're doing everything in letters, we're not doing the thing where we'll do similar problems and then you change the numbers like we do for, like you do for your students, or I do for my students in University of Physics 1. But what we can change is initial conditions. So we could have the same differential equations of motion, but the initial conditions then change what your particular situation is going to look like. So in this case, we're saying V naught equals V naught x hat. Now our forces we're going to say is that we have a linear drag force. So that's minus CV, and we have gravity. So this is what's kind of tricky about doing drag in 2 dimensions, is that the drag force is in the opposite direction as the velocity, and the velocity is changing direction, so the direction of your drag force is changing. So it actually turns out if you try to do this with a quadratic force, and you can look at this in your book, if you do a quadratic drag force, that we end up with differential equations that we can't solve without a computer. But we can do it for linear resistance. And then gravity is in the y direction, as usual. So what's our equation come out to? Alright, well here's the thing. Okay, so velocity can be written as x dot x hat plus y dot y hat plus z dot z hat. So when we plug that in for our velocity, we get this. So I want you to go ahead and write out your 3 equations of motion. So one for each component. You'll have an equation that comes from the x hat components, one from the y hat components, one from the z hat components. So go ahead and try those out. Alright, so we have our 3 equations of motion. So this looks like it should actually require all 3 dimensions to solve. But here's the deal. We know that the initial velocity is in the x direction. We know it's going to start moving in the y direction because we have this minus mg term. It's going to start falling, so it's going to start accelerating whether or not there's any velocity. So this, we still just end up with z is 0. It never changes because there is no z dot to begin with in this problem. If there was z dot to begin with in this problem, then we would need all 3 directions. But there's no point in doing that because you can just define x and z to be in the directions you want them to be to make your problem easier. Alright, so we have our 3 equations. We only really care about solving these 2. Now you know how to solve these. The x double dot, the acceleration of x only depends on the velocity of x. The acceleration of y only depends on the velocity of y. Now remember that we just solved for velocity before, right? Because if we don't need to use second derivatives, we're not going to use second derivatives. That is still true. So we're going to solve for a velocity. So use the origin as your initial position. Keep that in the back of your mind. You're going to need it later, but what I want you to do now is solve for each velocity as a function of time. You know how to do this. Okay, take a few minutes, give that a try, or go figure out how to adapt your old notes. Alright, so the first one is, okay, this is a separable differential equation. Let's do it. Integrate both sides. Okay, there's v of x as a function of t. Let's do number 2. So I've gone ahead and divided the whole thing by minus c because I don't want anything attached to my vy. Now in the y direction, our initial velocity is 0. So I'm looking at this and thinking, I made a sign error somewhere because this tells me that my velocity is in the negative direction. And velocity should not be in the negative direction. That would mean it's going up the way we have things defined. Let's look for my sign error. So at the very top step up here, I divided through by minus c. That means a negative sign should have popped up right here when I did this, which means this should be a negative. Alright, so now we have a form of equation that's approaching a terminal velocity. So let's write out our solutions together. Okay, so there's our solutions. Let's make sure they make sense. So it says in the x direction, it's steadily slowing down. In the y direction, it says it's speeding up, but eventually the speed's going to level off and reach a terminal velocity, mg over c. So I want you to find x of t and y of t. So again, you've done this sort of problem before. Now we just have two sets of equations. So it's twice as much work. Right, let's take a minute and figure that out. So to get x of t, we just need to integrate, and we're setting the origin as our initial position. Okay, there's x of t. So I've taken a writing v naught x, but we've decided that since the initial velocity is only in the x direction that we can just call this v naught. But there you go. So then our position as a function of time for the x direction looks something like this. So there's a maximum position just limited by x. The maximum position isn't just limited by when the y equation tells you it's going to hit the ground. Okay, now let's do y of t. Alright, so we get, okay, so you get this complicated function for y as a function of time. So in the y direction has a linear term and it has exponential terms. Okay, so when you consider the path the projectile is actually going to take, so ordinarily we would say if we're looking at the trajectory, y is a function of x, then the trajectory would look something like this. It would be a parabola. But now, because there's drag, it's going to fall under this curve somehow, and so it's not going to go as far as it would without drag, which you could probably guess. Now actually solving for y as a function of x is a mess, and I'm not going to make you do it. I prefer you just reason with it and think about what your x and y equations are doing and think about what that means for your picture. This is a situation when you start having a differential equation for each vector component. It's really nice to use computer tools like Mathematica to look at your results and to do a lot of your calculations because they start becoming really time consuming. But I hope this helps you get a feel for what projectile motion looks like when there's drag present. Your book has some more nice examples on this topic, and I encourage you to look at those as well. Of course, there's the interesting question. Let's say if you launched it with some initial velocity in this direction and it went like this, well then, where would it go? And then you might be thinking, all right, well, we know that we get maximum range when there's no air resistance at 45 degrees. It's actually less than that when there's air resistance, and it would be fun to figure that out as well. Here's one big takeaway. At this point, doing computational physics is really useful. Using tools like Mathematica and MATLAB to do your calculations is really useful because, as you can see, you just get so bogged down in doing the calculations that reasoning about what your equations mean and what your graphs mean. And you've just taken so much time doing your calculations that you don't have as much energy left for what's really the interesting part. And what's really important to think about is what your equations mean. That's what I really care about your ability to do, and I think that's what's really valuable for any physicist or engineer. There is another way of doing mechanics entirely, and we'll get to this after the next unit. Our next unit's rotational motion. The one after that, we're going to go into Lagrangians and Hamiltonians, which are a completely alternate formulation of how to do mechanics calculations. And when we get there, you can see if you prefer them over solving these. Okay, let me know how you're doing, and I'll see you next week.